today we're going to get into networking, which is the start of Module 5. And then we're going to get also into sensors, actuators, and computers. So I have two PowerPoint presentations I use for this module. There's only one chapter in CDX for this module, that's chapter 56. We're also going to have our electrical test in this module. So the electrical test covers everything we've talked about from Module 2 all the way through Module 5. And the questions are pretty evenly distributed among the different modules we've covered. And the questions come from the previous quiz questions that I've asked you in Canvas. They're not coming out of the CDX test bank. So these are things that are important to me that you know, remember, and that you learn from the class. And I also give you 2 chances at the test. So I will be sending an announcement out for when the test is going to be. I will also notify everyone in Canvas when the test is. And the test is open for just under 2 days. So you get 2 attempts, but you can only do it in that time period. Anyone who has not attempted the test or completed the test at least once by the end of the first day, I normally send an email to reminding them to make sure and do the test. Because like I said, the test is only open for a short period of time. It's the only assignments I have that really have a real small time window in which to get them done. And that's why I generally give people a week's notice when that's going to be happening. So I'll be looking at the schedule and seeing how the PowerPoint's laid out. And tentatively, I'm thinking it might be next Wednesday and Thursday, but I may carry it into the following week. So that's what we're looking at as far as our test. Any questions on the test? The ones I normally get is how many questions is there? There's 50. The other question I get is, are they multiple guess? And yes, they're multiple guess. So yeah, there are 50 multiple choice questions. No other questions on that? So, all right, well, we'll get an announcement out probably tomorrow. I got to go down to campus today. So I'll look at it. And like I said, it's either going to be next Wednesday, Thursday, or I may carry it into the following Monday, Tuesday. So I'll get something out on that. But just to give everyone a heads up. So vehicle networks. Networks have evolved from very simple networks that just allowed our engine and transmission to communicate with each other. This allowed the computer to now control the shifting of the transmission. And from there, it evolved into traction control systems. So we started involving the ABS system. And once we did that, things really kind of took off. And so vehicles today have multiple networks and lots of modules, because we found that as we share more information, we can provide more features on the automobile, because we already have sensors to do these things. So many times it's only a matter of installing an actuator, or sometimes it's just a matter of installing programming, because we already have all the things the computer needs to carry out an action, all the things the computer needs to see what's happening to make a good logical decision. They just hadn't put that programming in yet. So we've seen just really an explosion of networks, certainly in the last 20 years, but even in the last 10 or the last 5, it is just exponentially growing. We talked about our advanced driver assist systems and autonomous vehicles. Those are heavily networked. Again, they have to rely on a lot of information to make decisions quickly. And we don't want to have 5 sensors telling 5 different computers the same piece of information. We'd rather have one sensor that gets that information to a single computer and then puts that information onto the network system. Or a lot of times what we see is the sensors themselves are actually modules. They're actually small computers, and they're talking directly onto the network. So we're going to look in here at networks, form, and function. I'm going to start out with the basic kind of what a network is, how it works. Data packages, communication. Then we're going to go into some of the different protocols that we use. So when I talk about networks, there's two parts to a network. One is the physical construction of a network, how it's built. The other is the language that's spoken on the network. So I can build a network many different ways. And in each of the ways it's built, I have the potential of using different languages to communicate in that network. So some languages, such as all 2008 and newer vehicles in the United States, have to use a particular language to talk to the OBD2 system. That's required by law. So every vehicle uses that same language and the same what we call protocol to communicate. However, the construction of the networks can be very, very different. So the physical construction is still allowed to be very different, but the language has to be the same. So when we're diagnosing network problems, we need to look at how is it built, physical construction, and know what language it uses. And by knowing what language it uses, now we know the electrical parameters of how that language operates. So even though I can't speak that language, by knowing the protocol, I know what rules that language has to follow. And then with using a lab scope, I can see when something's not following it correctly. So for many years, there we go. For many years, as vehicle manufacturers added new features to their vehicles, they had to add more sensors, actuators, wiring to accommodate these new features because everything was developed as its own separate system. These additions added more complexity to the vehicle, required a larger and more expensive central computer. So as we added things, we either add things where we had multiple computers, they don't talk to each other. So there are cars with 3 or 4 different coolant temperature sensors, one for each system. Several different speed sensors to see how fast the vehicle is going, one for the transmission, one for the speedometer, one for the, or 4 for the ABS system. So we had a lot of redundancy in different sensors, really conveying the same information because different modules needed that. And so the manufacturers started out with really one computer in a car, the engine control module. And so we started adding things to the engine control module. Then the decision had to be made. Do we want one central computer on a car? Or do we want a lot of smaller computers? And the decision was made to go with a lot of smaller computers for a couple of reasons. First of all, not all cars are made the same. So if I put a big computer in a car, it need to be the biggest computer I might ever need based on if I put on every feature. So there's a lot of cars I would be putting in more money than I need to put in. The other is with one computer, if it goes down, everything's down. It's all or nothing. And unlike our home computer, that if it goes down, it's frustrating, it's inconvenient, we lose data and so on. On a vehicle, if things go down, we could have a catastrophic problem. So we don't want everything to go down all at once. Also with networking, with having a lot of small computers, we're able to share computing resources. So we're actually able to build a bigger computer modularly as we add more and more computers to the network. We're able to do more things, have more computing power, and perform more functions all at the same time at a much lower cost to the consumer with much higher reliability. So that's why we went that way. So before electric cooling fans were first controlled by the PCM, it was not uncommon for an engine to have 3 coolant temperature sensors or switches, one for the coolant temperature input to the engine control module or powertrain control module, one for the electric cooling fan, turns the fan on and off so your car doesn't overheat, and one for the coolant temperature gauge or warning light on the dash. So we'd have 3 sensors. So if I want to diagnose the system, not only did I need to find the coolant temperature sensor, I had to find the correct one and make sure I'm working on the right one for the system I'm trying to diagnose. So it was more confusing for the technician. We had 3 times the wiring, 3 times the sensors. So your manufacturing costs went up, the weight of the vehicle went up. So it was much simpler to put in one sensor and then share the information with everyone who needs it on how hot the engine is. One thing that I left out here also is I need to be able to turn the fans on when I turn the AC on. So now we're up to 4 different types of sensors. So you can see where this really was snowballing as we started making more and more functions electronic, because on an old car, 1960s, 1970s, most of the functions were mechanical. And up until 1974, even the ignition system, although it's electric, was basically a mechanical system that was controlling the electricity. We hadn't gone to solid state yet. We hadn't really, one thing with transistors in the car was the radio. So, everything was, real isolated, still largely mechanical, so our electrical is really confined to supplying power to our ignition system, supplying power to the lights, starter, alternator, battery. We didn't have a lot of electrical on the car compared to what we do today. Those extra sensors were redundant, added weight, which meant less fuel economy to the vehicle and added more potential for system failure, shorts, opens, etc. The theory being that the more connections we have, if 0.01% of connections go bad, the more connections I have, the more chance that car is going to have a problem. So by eliminating parts, eliminating connections, even though the parts aren't any more reliable necessarily, there's just fewer of them to cause a problem. To eliminate these problems, manufacturers change to a network system. So a network system can use a single sensor for many modules that need the same information. Is that true or false?
True.
It's true. So here's an example of some of the different modules that we might have on a vehicle. This is not everything that could be on a vehicle. And some of these modules are mutually exclusive from each other. However, this gives you just a small idea of the number of modules that we could have on a vehicle. Like I said, a 2018 Porsche Panamera fully loaded had about 168 modules. But you can see here where we have everything from it, we have some adaptive lighting, adaptive cruise control, adaptive braking, electronic power steering. So you see where a lot of these ADAS type functions are really exploded the number of modules on the car. But we have our TPMS, seat position control, transmission control, keyless entry, our OBD2, so we can see there's a lot of different features we can have. And this is just a few of them: battery management, entertainment system, windshield wiper control, engine control. And we put more here, except for there's not room on the page. So this gives you an idea of why we have networks. And many of these systems need some of the same pieces of information. So we call these networks a local area network. It's a generic term. So a LAN network or local area network is not a protocol. It's just a way of describing a local network. So the advantage to having a local area network system eliminates hardwiring of sensors and actuators to every component, such as the PCM, warning lights, fans, etc., which results in lower production cost, better fuel economy, which means lower emissions. Eliminates redundant components and wiring, which reduces vehicle weight, reduces potential system failures, open shorts, etc., since there's less wiring and less connections. And the information transfers faster between the component systems. Because these systems are working so fast, we're able to convey that information in what we would see as real time. We're sharing that information in milliseconds. Which of the following is an advantage of having a network system on a vehicle?
All of the above.
All the above, absolutely. Less vehicle weight, better reliability, and better fuel economy. And even though our cars are far more complicated today than they were 20 years ago or 30 years ago, they're more reliable than they were 20 or 30 years ago. They're better. They're more reliable. We can get more miles out of them with fewer issues. So if I'm going to have network communication, I need to have some rules, or else my traffic might look something like this. So how does all that information get transferred on a single wire or two-wire network? Well, because there has to be a priority in the communication. Some modules like the airbag might have higher priority if they're telling you we just fired the airbags than requesting the air conditioning, or I'd really like my driver's window to go down. So different messages have different levels of importance, priority. So the modules, when they broadcast a message, certain modules have a higher priority than other modules, but also certain messages have higher priority than other messages. And if you think about it, isn't this how we communicate is people? If we're in a group of people, you listen, you take turns, you exchange information. But if something is really important, a lot of times that has a way of everyone will stop and listen to what that really important message is. So if people are sitting around talking and the fire alarm goes off, or we're hearing that through our ears, it's another input to our system, just like the person next to us talking would be. But that would have a higher priority, be like, oh, there's a fire alarm, we need to go do something. We're going to suspend the other conversation. So our networks are able to work the same way, just like the cable coming into your house. If you have cable for your internet, TV, telephone, we're putting all those things on one wire through the cable. But yet, because of the digital language, we're able to get internet, telephone, and TV all at the same time. So in general, the system deploys what's called a data bus with one or two wires to carry individual information packets, sensor outputs, computer commands, etc., through the network. So our multiplex network system, think of the bus as a freeway with on and off ramps to cities, i.e. modules that can exchange information. The cars are like information packets traveling on the bus. The information is only delivered to the correct destination. So if we have information, it knows which modules need that information, and that's where programming comes in. So when we replace parts on these vehicles that are attached to the network, many times we have to either do what's called version coding them, letting the module that's installed know who else is on the network. Sometimes is it gas or diesel, right-hand drive, left-hand drive, and so on. What country am I in? So your version coding is very popular with European models because they'll have one part number that controls the climate control system for that model for the entire world. But there may be 10 different versions of it. So it allows them to make one part number, one physical part, but it does the job of 10 different parts because it gets coded once it's installed to the vehicle and told how to work and who to talk to on that vehicle. Domestic manufacturers and some Asian manufacturers tend to use what's called programming. And that's a little bit different because instead of just flipping switches with a scan tool telling it what version to use, I'm actually having to contact the manufacturer's computer and download software for that component to work properly in that vehicle. So for example, if I put an instrument cluster into a Chevrolet truck, and I get it pre-programmed where it has the correct mileage in it and all that stuff, the speedometer and all the functions are going to work. But when I go try to use my steering wheel controls for the radio, for some of these other things, they're not going to work because the module is not programmed to know that I have steering wheel controls. That has to be programmed on the vehicle. So it's not uncommon to put a part in and have something not work afterwards. I put a climate control module in a BMW once and the power windows didn't work until I version coded it. So we do see some really unexpected things because of how manufacturers put together their networks. And so that is why we program or version code modules when we install them in many cases, because the module needs to know, A, who else is on the network, and B, am I supposed to give information to someone else on the network? So for example, I was teaching a network class this last weekend, and one of the case studies I use is a Ford truck, and the speedometer doesn't work. Well, the information out of the manual says that the speed sensor on the transmission is supposed to work the speedometer. And the speed sensor on the transmission works great, but the speedometer doesn't. So we went and checked the ABS module, since that also has wheel speed sensors, and it worked great, but again, no vehicle speed signal. And we proved the speedometer worked in the dash and all that stuff. So once we figured out that everything that can measure how fast the car is going or the truck is going works, but no one is putting a speed signal on the network, we started looking at programming. And what we found is someone had put a used ABS module in the vehicle, and it was not programmed to tell the instrument cluster how fast the car is going, or tell the engine computer how fast the car is going. So on the truck, depending on whether it was 2 or 4-wheel drive, it either used the output speed sensor or the ABS module. And what happened is they took a ABS module from a 2-wheel drive truck, put it in a 4-wheel drive truck, or vice versa. And so consequently, it wasn't programmed to work correctly in that application, even though it bolted on, fit, you know, the ABS lights off, all that stuff. But it wasn't told that it was its job to convert the wheel speed sensors into a vehicle speed signal and put it on the network. So therefore, no signal ever got on the network. And those are the kind of issues. So we program things to let them know who else is in the neighborhood and what their job in that neighborhood is. And that's why modules have to be programmed. Do all modules get programmed? No, they don't. But many modules do, and that's normally an additional charge on top of the module replacement labor. And normally that's $100, $125, $175 to program a module. Some are even more. Oh, I see what I left out. That's why I got these questions, is to keep me honest. So computers can only display or talk in digital language, ones and zeros, right? So an analog signal is, gee, I can go up to 1 volt, 2 volt, 3 volt, 4 volt, 9 volt, 12 volt. I can vary what I'm doing. I'm not fixed. Digital is very strict. It's ones and zeros. So computers only talk in a digital language, ones and zeros. Now, when we put this information on the bus, we put it into what's called a packet of information. So this is an information bundle, or like putting a letter in an envelope. And so packet data goes way back. Amateur radios used packet data forever. And this is something that we incorporate in the network. So a module puts together a packet of data, and that packet of data will say what the priority is, who's it from, and who it needs to go to, and whatever information is involved. And that packet gets put on the network, and then that packet is delivered to whoever it's addressed to. And that packet is going to be full of digital information. And now this next question should make a little more sense.
Number 4.
Number 4. And that's another reason why I put these questions in here sometimes, is to keep me on track, to make sure I don't leave out something that's important. So these are packets of data. So when we look at network traffic with a lab scope, we'll actually see these packets of data on the network as it communicates. So we can actually see when it talks and when it stops talking, when it talks. So we can see each of these packets go on the network. And depending on the protocol, the packets will look slightly different. But we can always tell when it's information being sent. So here is a simple looped series network. So we have different kinds of network construction. This is a loop series network. We also have what's called a star, where we come from a central point and go out. And I've got pictures of the different ones here. I think I put a star in here. If not, I'll need to. So this network here, we have the diagnostic link connector where our scan tool would connect, and it comes over to our HVAC module. And then from our HVAC module, we go to our cluster, our memory seat module, and our radio module. So this is a simple network, and this particular one happens to have 1 wire, but I can build a network this way using 2 wires. I could build a network this way using fiber optics. I mean, there's no limit to the technology I can use. So this is the physical network. Now, this network provides some advantages in that if this wire breaks, then the memory seat module could still talk to the radio, which talks to HVAC, and the cluster could talk to HVAC. So the cluster could still talk to the memory seat module going all the way around the long way, depending on the protocol rules. So some protocols, like the single wire protocol, allows communication in both directions. No big deal. If it can get there, if it's connected, we can send a message. Other networks that use this structure only go one direction. They might just go counterclockwise. So if there's a break, all the HVAC module will be able to do is hear from the cluster. It couldn't hear from either of these because the break's here and it's only allowed to go counterclockwise. So you see where, the physical structure we use to figure out where we might have a break or what might be a problem based on who can and can't talk. The protocol determines the rules that talk has to follow. And that also helps us in our diagnosis and our testing. So here's a looped series network. Here's an example that has a couple different series networks. So this has a looped series, and this also has some straight series networks. And what I've done is I've highlighted a couple. So here's our pin 2, like we had in the last picture, except for here it goes to a splice and goes to a lot more than 4 modules. So if I'm trying to figure out how this system works, I'd want to use some highlighters, because the highlighters I can use to kind of demonstrate some different ways that communication might happen. So here I could highlight in blue. So if I have a problem in the blue wire, or the blue wire is broken, I'm not going to be able to talk to anybody, because that's the wire that goes to the DLC. So if I hook up a scan tool and I can't talk to anybody, and I'm looking at an open circuit, certainly either the DLC or this blue wire has to be the highest priority. Because if there was a break after this splice, I'd still be able to talk to what? Some of the modules. And so if I can't talk to any of them, just by looking at the schematic, I know the problem either has to be my scan tool, the DLC, or that wire. As I look up here in the yellow, this is what's called a daisy chain. And we can daisy chain in a loop or just daisy chain in a series. This is a method we use in a series network. And what we're doing is we're taking a signal going into this module, the same signal is coming out to the next module, and so on. And we see I did the same thing here with the green, where we got daisy chain from here to here to here to here. So if this wire broke right here, I wouldn't be able to talk to this module, this module, this module, or this module. If this wire broke here, I'd still be able to talk to the first 2, but not the second 2. So you kind of get the idea based on how it's built and which modules I can't talk to. I can start figuring out what might be wrong or where the problem might be. So even though networks sound really intimidating, it's really about who can't talk to whom. Now here I have a loop in the purple. So the purple, I drew a loop, comes through this module. These are still daisy chained through here, down, and I can come all the way back down through here, and get back to my starting point. So it is one big loop. I'm not sure why it didn't get highlighted. Here is another little loop. I did this one this way. I could have gone either way. Back to the splice. So you see I have several different little loops here. Now, this is a single wire network. I could design this as a 2-wire network. So even though there's 2 wires going to the module, it's only a single wire network. To be a 2-wire network, if I was daisy chained it, I'd actually have 4 wires going to the module. If it's what we call a star network, where we come from a central point and I have wires going out to each module, then I'd only have 2 wires going to a module if it was a 2-wire network, or 1 wire if it's a single wire network. So here's a wiring schematic, and I can use a wiring schematic to develop the layout or figure out the topography of the network. Some scan tools also have what's called a topography screen. So in this case, we can see that I have a DLC, I have a module. From this module, I have a network that goes out, and then it goes to 1, 2, 3, 4, legs, 5 legs, I guess, if I get that optional one. And then in the middle of this leg, there's another splice that comes off. Then I have this network over here. So it comes off and it goes to 2 modules. Here it goes off to a bunch of different modules. Again, a bunch of, so where we're seeing a point and it goes to a whole bunch of different modules, we call that a star configuration. Goes from a central point and goes out. So this is what we call star networking. And star networking is nice because I can go to that central point and I can start disconnecting or testing things. It also kind of, again, can help me who is there and who isn't there. So in this example, because all these colors do actually mean something, and the gray means it's not there. And then we have the blue, yellow, and red. And the red means it's supposed to be there by the VIN number. This car left the factory with it, but that passenger door module is not reporting. So in this case, we're able to see the problem with the passenger door module either has to be the door module itself or the wiring coming to this splice. It can't be anywhere else because that's the only module that's affected. So this is where topography is really helpful. Now in this particular vehicle, we have 3 networks. I have a network right here in purple between the DLC and what's called a gateway module. And then I have the high-speed CAN network right here, which goes to my powertrain control module, transmission, ABS. And then I have another network over here in blue that's a little lower speed network that goes to a lot of my body control, radio, and so on, sunroof. So I actually have a total of 3 networks on this computer, and 1 network is only used by my scan tool. So this topography screen shows me the different networks, and it also shows me how it's kind of put together. This is not a wiring schematic. Now this happens to be a 2-wire network. Both of these are 2-wire networks, but we only see 1 line connecting everything. So this is just an idea of how it's put together. And we use this to kind of figure out relationships if things aren't working. Anytime I have more than 1 module not working, the first question I have to ask is, what do they have in common? Do they, daisy chain off on part of a network? Do they use the same fuse? Do they use the same ground connection? What do they have in common? Because odds are 2, 3, 4 modules all didn't decide to go bad at the same time. So therefore, whatever is causing multiple modules not to communicate or not to function is probably not that you have 4 bad modules. It's probably something that the 4 modules have in common. And that's why we go through these steps of looking, how is it built? What do things have in common? Remember, it's all about asking questions. It's not about jumping in and ripping a car apart. It's about asking questions and making comparisons, just like we did in our lighting circuits in the electrical section, or like we did in the other things, is right. We're going to step back, we're going to analyze, let's see how it's supposed to work. Let's see what's not working, and then ask questions about what might be the cause. So a vehicle may have more than 1 network. Is that true or false?
True.
True. And if you put false, you must have slept through the last slide. Another name for a network structure is which of the following terms?
Number 3.
Number 3, topography. You guys got it. So I have a little case study here. And this is a vehicle that the customer had an intermittent problem of it not starting and the accessories not working, like the seat, the windows, things like that. And the customer didn't want to leave the car. So we pulled the codes out of it and, and got the information to see if there's anything there. And there really wasn't anything, any codes, anything else. So we had nothing there. And there's 15 modules in the network. So there's 15 modules, anything's possible, and no codes. So next thing we did is the customer didn't want to leave the car. So the customer took the car. The next day, the car got towed back in And when we connected the scan tool, this is the message we got: no communication with the vehicle. And the car doesn't start. Well, yesterday we were able to communicate and the car started. So I'm guessing that the fact that I can't talk to any of the computers has something to do with the car not starting. Right? I mean, that's a reasonable assumption. I could talk to it yesterday and the car ran. Today the car doesn't run and I can't talk to it. So it makes sense those things are quite possibly related. So anytime I can't communicate, what I'm going to do is I'm going to check pin 16 for power, pin 4 and 5 for ground, and then I'm going to go to whatever pin is used for the network and look at it with a lab scope. In this case, this is an older GM and it uses pin 2 for what's called class 2 data or class 2 communication or J1850 data. There's a lot of names for the same thing. But how this works is it sits at 0 volts and goes to 7 volts when there's something to be said. So there's a transistor in the computers that are able to toggle from the 0 volts, that's the at-rest voltage, no one say anything, to 7 volts when a computer's saying something. So we hooked up a lab scope and we looked at the capture here, and here is 0 volts. And it tells me that each division is 2 volts. So 2, 4, 6, 8, 10, about 11 volts, kind of close to 11 volts there. So if I have 11 volts, can anyone hear a computer trying to go from 0 to 7? No, because all I have is 11 volts. So you have no communication possible because there's 11 volts on the wire. Now we know why we can't talk to the computer. Now we know why we have a problem. So the next question is where's the 11 volts coming from? For that, we need the wiring schematic. So we go to the wiring schematic and we find our pin 2. And we find that the wire is connected to what's called a splice pack. So this is a star network. So this has a splice pack where all these different computers are connected to. So this makes it much easier to try to isolate the cause, because I can go to the splice pack, take the connector out the back of the splice pack, and now no one's connected to anybody. And I can start testing to see which pin has the 11 volts. And that's what we did. So we went to the splice pack and we went to the different pins, because I took the back of the splice pack out, went to the different pins, and we found the pin with the 11 volts. Once we found the pin with the 11 volts, then we go back to the wiring schematic and we look at where that pin is. In this case, it's pin H, and pin H goes to another splice pack, in this case, splice pack 206, that happens to be in the B pillar behind the driver's seatbelt assembly. So we got to do a little more disassembly now. So we get to that splice pack and we find the pin, take the back out and find the pin with the 11 volts. Then we go to the wiring schematic and we find that pin C is the one with the 11 volts. So the 11 volts has to be coming on this wire, and at the end of the wire is the memory seat module. So it has to be somewhere between the memory seat module or a bad memory seat module, something shorted inside, or something in the wiring. So what we did is we looked for test points now. And if you see, I have different connectors. So connectors are always good test points. So what we did is we went to connectors 321 right here, and we disconnected the connector. And when we did, our 11 volts went away, which means that my problem has to be either the memory seat module, the wiring, or the connector. So if you're thinking about just throw a memory seat module in, slow down a little bit, right? Because that's only one possibility. Is it possible that we could have a problem in the connectors or the wiring? Absolutely. So we don't want to just start throwing a part at it. We want to isolate it. So the next step would be to what? Plug this in and unplug this. And we did that. And guess what? We still had the 11 volts. So we wiggled the wires with it connected and found that we could get it to go up and down, up and down. So we definitely had a connection problem. We localized it to this connector. So we took the connector apart and we found this little green stuff here. And that green stuff was between pin 8, which is our data pin, and pin 7, which is the pin that has our battery voltage. So this corrosion was making an electrical connection between pin 7 and pin 8, allowing 11 volts to be on that network wire. Could you see where someone could put a lot of parts in this car and not find that? Yes, no?
Definitely.
Yeah, I mean, that's really kind of a unique thing. It's a needle in a haystack. And it was found because the technician did not jump to conclusions. We always want to prove what's wrong, not just think what's wrong. We don't want to go, well, this is probably it, or I'll try that. Probably the hardest thing to teach young technicians or teach students is that they're really anxious to fix a problem. So they can't wait to go buy the next thing to put it in to see if it fixes the problem, instead of slowing down and let's actually analyze the problem and find out what's causing it. That patience is a taught thing. It doesn't come naturally to us. So, going through and being methodical and really playing with it to isolate exactly where that problem is. And what's interesting is I have a lot of customers still that will ask me, well, if I have you do the repair, are you still going to charge me for the diagnosis? Or you're going to charge me diagnosis just to look at the car? In this example here, where was the skill? In cleaning the green off of the plastic, or in finding that the green was the problem causing the car not to run? Where's the higher level skill here? What should we be paying for? In my feeling, we should pay for both. We should pay for finding it and cleaning it. But you see kind of how ridiculous that is to ask, gee, if I have you fix it, are you still going to charge me for diagnosis? Well, sure, because diagnosis is different than repair. It's a different task. It's a different knowledge, different skill level many times. I could have anyone clean this off. I couldn't have anyone find this. So again, it comes down to that value of diagnosis. Good diagnosis is very valuable. Unfortunately, there are plenty of shops that charge for diagnosis, but don't do a good diagnosis. They have bad habits. And that's why it's hard finding a shop. And that's why certifications such as ASE and other things are really important to look for when you're having your car service. So like any repair, when we're done, we want to verify the system is operating correctly. So here's a scope capture right here, and I'm still on 2 volts per division. So here is my ground, 0 volts. And if I come up 2, 4, 6, we're toggling right about that 7 volts. We have a 0 to 7 volt range. And it's normal to have some messages that don't go all the way to 7 volts. And that's part of that priority, part of that message structure. So that's very normal. They need to go more than 80% of that value. So I need to get up past at least 7 volts to 1.4. So that'd be 5.4 volts? No, 5.6 volts. So I have to get above 5.6 or it won't see the switch. And we're easily doing that because here's our 6 volt line. So this is normal communication. And these are all little packets of information. Isn't that amazing that we can say something in just these few lines? I don't know. I mean, to me, that just amazes me that we can actually, here's just this little line moved up and down, and yet it puts a piece of information that a computer can understand.
Yeah, once you start grasping the knowledge, it's really cool to start seeing, it's right there. The more you know, the easier it is to communicate. It's really cool.
It is cool, isn't it? And that's why I put this case study early on, because it is one of my favorite case studies because of what we found that's wrong. But I also really like that it really kind of shows the process And it shows I'm not doing anything magical. I'm using the tools that we've already learned in this class. I see my dog has something that it's very excited about. Using the tools that we have in this class and using what I'm showing right now, which is that network wiring schematic, going back to the wiring schematics we learned in the previous chapter, and showing the schematic going through. So let me see what is up. Hey, get in here. Yeah, I can't even hear. Got it. Okay. I don't know why she was so excited, but she's not as excited now that I went out and yelled at her. So, but no, it's neat. I mean, so hopefully it's kind of putting some of the things we've been working on the last couple of weeks together and kind of showing that practical application of how we go. Like I said, I don't need to know what's being said here, but I know something's being said and it's following the rules for this network, which is 0 to 7 volts. And I can see I have packets of information. So when I'm at 0, that means nothing's being said. So this is a normal pattern. So the class 2 data system that we just discussed operates in what voltage range when it's toggled high and low?
7.
Number 3.
Number 3, 0 to 7 volts, correct. And the reason why I put this in here, you're kind of like, why is he picking on just one network? This was used by all GM vehicles until they went to the controlled area network system. So GM used this for a number of years, and there's a lot of GM vehicles out there. So this is a common system to work on. Plus, this is a common system to have issues. Just because there's a lot of GM trucks, a lot of GM vehicles. GM was of the domestic manufacturers, really started networking a lot of things very early. So they started using this early. And so we see more network issues with GM. Their code detection's a little better, and they had a lot more stuff in the system. I mean, 15 modules back in the early 2000s was a tremendous number of modules for a car to have at that time. So GM was kind of ahead of the curve on it, and consequently, we see more failures and more issues with them. So the class 2 network uses how many wires for network communication between the modules and the DLC?
Number 1, I guess.
Yep, number 1, it's a single wire network. Absolutely.
Yep.
Absolutely. So that is an example of a one wire network. Our newer vehicles that use controller area network for PCM communication we're going to see as a 2-wire network. So we're going to get a chance to look at that also. So CAN, controller area network. There are different types of CAN. Low speed CAN can be a single wire network. Medium speed and high speed CAN are going to be 2-wire networks. And if it's a 2-wire network, it's going to be what we call a twisted pair that I'm going to show you in a minute. So all manufacturers now use a network system called CAN, or controller area network, for OBD2 communication. This system was required on all light duty vehicles sold by model year 2008. There was a couple exceptions like the Crossfire and one other one, because that was the last year they were sold. So when it comes to OBD2 communication, and I want to talk to my PCM, by law, every manufacturer has to use this high-speed 2-wire CAN system since 2008. So 14 years now it's been required. Vehicles first started using it for OBD2 communication for generic OBD2 in 2003. There's some manufacturers like Volvo that used it for OBD2 communication back in the 90s. And CAN has been around, 1992 was the first production vehicle in the US that had CAN. In this module, there's an article on CAN done by Bosch. It has a lot of pictures, so even though I think it's 20 pages, at least half of that's pictures. But it is a really good article. So it's a homework assignment. So there's an article and a quiz after the article. And so it really talks about networking, it really talks about CAN, and Bosch does a good job of really drilling down. So that is one of the assignments I have in Canvas for this module. And I think you'll find it really helpful. It's a good article. I like it. I used the older version, then they updated with this one, and it brought it current. The advantage of the system is that all devices will have standardized communication protocol to the DLC. So your scan tool will be able to communicate with this high-speed network, regardless of what kind of car you're working on. So this has been good and bad. Before CAN, I had to have a more expensive scan tool to talk to the different protocols. And so I might not be able to really talk well to some of the European cars, or that I could get some basic information. Prior to OBD2, manufacturers, in order to talk to their computers, used all kinds of different ways of doing it. So if I, jump back 20 years, I had to have a tool just for talking to European vehicles. Because otherwise I wasn't able to work on them. And so most shops didn't have that tooling. So the number of people that could work on European vehicles effectively was much smaller. With CAN, and with OBD2 first, and then with CAN second, it's really standardized things to where we've seen the cost of tools come down, which gives more people access, which I think is a good thing. On the downside, everyone now thinks they're an expert. So everyone thinks that everything's the same because their tool hooks up to it. So although a Mercedes and a Chrysler have similarities, they are different. And a Chrysler is very different from a Ford, although it has similarities. So as we, do different manufacturers, even though some of the information we see is the same, it can mean very, very different things. And so unfortunately, now everyone thinks they're an expert on everything, and that's really not the case. But it has allowed people to work on more kinds of vehicles, and it's gotten rid of some of that specialty. So the CAN bus wires are in a 2-wire configuration with positive and negative. Each wire is capable of transmitting information. Matter of fact, they transmit the same information. It's redundant. So when the computer receives information, it's looking, did I get the same message here as I got here? If I didn't, something's wrong, I'm going to set a code. So code setting for these systems is really good. It's able to recognize if there's issues with the system. The wire is twisted to reduce stray or induced voltage signals coming into the bus from adjacent high voltage sources, secondary ignition, coils, your stereo system, and so on. So not all CAN is a twisted pair. So low speed CAN, which is a single wire network, there's nothing to twist it to. Our medium and high speed CAN systems are going to be twisted pair. If we look at our ultra high speed CAN systems, it may be a twisted pair if it's electrical, if it's copper, but we also use fiber optic. We use some other things when we get to ultra high speed stuff. So by twisting the pair, it creates shielding. So the number of twists per inch determine the frequency that the wire is protected from. So this is not just a random twisting. It is actually done in twists per inch, and there's actually a chart somewhere that the engineers use that this to protect from this frequency range, you need this number of twists per inch. So if you're repairing these systems, you want to make sure you put the same number of twists per inch in. So connected to the bus are modules. Many are programmable, and these modules are all small computers. So we see the term module, which is what we use in automotive. We see the term node, which is computer talk, which is there to confuse you, which is just a module. And we also use the term computer. Well, a module is a computer. So you can see where we have three names to really describe the same thing, just because it'd be too easy if there's only one. Most modules can receive information packets off the bus, like sensor and actuator data off ramps, and also send information packets like on ramps to travel on the bus to be used by other modules. So there are some modules that are not connected to the outside bus, but have a local bus. So in other words, I may have a loop of modules and they can only talk to the dominant module. And then that dominant module is on the network and can share information with other modules, but they can only share information with that dominant module. And so that creates the relationship of the module. So not every module is on the network, and not every module I'm talking to on my diagnostic device or scan tool. I might not actually be talking to the module. I might be talking to a dominant module that's acting like an interpreter. So using these modules eliminates the need to have a large central computer. In what year was CAN required to be used as the OBD2 communication protocol?
2008.
Number 3.
Number 3, 2008. Since most modules are programmable and use a standardized communication protocol, they can be programmed to accommodate any new sensor, actuator, or component as the manufacturer chooses to add during updates without extensive rewiring. So one of the neat things about these is these modules are potentially expandable. I can use the same module regardless of trim package, and we can add things to it by programming. The connector normally is a pretty large connector, so it may be 80, 105, 126 pins. We're not going to use all of those pins, so we're going to have some open spaces. So as the next model comes out, a manufacturer can change the wiring without having to change the connector or change the module itself. We can make internal changes to the module without changing the connector. Again, having a lot of updatability. So maybe I make a car for 3 years using a module. We add some new features, so I need to put some new programming power in that new module. I can do that moving forward, but I can discontinue that old module and just sell a customer that new module with more computing power, but program it to act like the older module. Modules can be placed at various locations on the vehicle in close proximity to sensors, actuators, and components they serve. So in the past, we would run our brake light wiring from our brake light bulbs all the way up to where the switch is on the brake pedal. And then from there, it would go to the fuse box where the power comes from, and then to the battery, obviously. A lot of wiring running the whole length of the vehicle. And then we had to do the same thing for tail lights going to the headlight switch and backup lights going to the backup light switch. So we ran all these wires from front to back. What many manufacturers do today is they put a module in the back of the vehicle. And now I'm going to wire those brake lights, tail lights, license plate lights, turn signals, all this into this module in the back of the car. And I'm only going to run the 2 wires from my network up to the front of the vehicle and power and ground. So my battery may be back, so I already have power and ground there, or I may need to run power back there, whatever. So now I'm running these network wires the length of the vehicle, and they're going to be connected to other modules. So now when I hit my turn signal is either a switch or it could be a module. But if it's a switch, it's talking to a local module. It says, hey, I'd like turn signals. That local module is now sending a signal through my network to the module in the back of the car, telling it to turn the turn signal on. I have another module in the front of the car that's getting the same message to turn the turn signal on. So now both my front and back turn signals are flashing. So this eliminates a lot of wiring. So we're able to have tasks completed locally. It also allows me to run wiring for a sensor to the module that's closest that's on the network. And then that module can put that sensor data on the network and share with other modules. So for example, if there's a sensor underneath the hood and a module underneath the hood, I can run that sensor information to the module underneath the hood, even though I have module underneath the dash that needs that information. But all I need to do is get it on the network and then I can share it. So you can see where exponentially we're using literally miles less of wire when we build a car today. Pretty amazing. We have more electronics, more things, but using fewer miles of wire. Each module is programmed to emit its data using electronic code. This coded data packet is given priority based on how important the operation of the vehicle. Wires are used as a twisted pair in order to prevent which of the following conditions from occurring.
Number 4,
Number
2,
four,
and 3.
induced voltage and signal noise. Well, signal noise is created by induced voltage. So number 4. So in this example, the engine coolant temperature sensor sends a low voltage signal to the module that is directly connected to, indicating an overheating condition. That module converts the analog temperature signal into a digital information packet to be sent out on the bus. The information packet is given a high priority code. In this case, it is given the high priority code due to the seriousness of the message. Each module, commonly referred to as a slave module, is connected to the master module. The master module sorts the information packets on the bus and decides the order in which the information packet should be sent via priority on the bus, like a traffic officer. Some of the slave modules are in sleep mode, and the master module has to wake them up. The reason they are in sleep mode is to reduce parasitic drain when the vehicle is not in use. So when I turn my car off and take the key out, I'd like the car to start when I come back. So my modules have to go to sleep, but I need to keep a certain number of them somewhat awake so they can wake the other ones up. So that's where we get into that dominant and non-dominant module, or master and slave module. So the book still refers to it as master and slave. We're seeing some of the new stuff use dominant and non-dominant module. And that's from Chrysler's new stuff. The master module is also sometimes called the gateway module. When the scan tool is connected to a vehicle, the CAN is often only talking to the gateway module, and that module will retrieve the information from the module the scan tool is trying to interrogate. So what we're talking about is, I'll back up a little bit here. What slide am I on? 43. So in this example, this is a gateway module. A gateway module is an interpreter, and it is able to speak 2 languages or more. So it is taking information from one network, processing, sorting, and transmitting it on another network. So in this example, if I want to use my scan tool at the diagnostic link connector to talk to the powertrain control module, even though my scan tool says I'm talking to the powertrain control module, in reality, I am talking to the gateway module. The gateway module is talking to the powertrain control module. So I am asking it for something, then it goes and asks the PCM. The PCM comes back to here, then it tells me. So on this particular computer layout or network layout, the only module you're ever talking to is the gateway. So it doesn't matter your scan tool says you're talking to 20 modules. You're only talking to the gateway, and the gateway is talking to the other module and getting the information you're requesting. So obviously, if the gateway module goes bad, nothing else works. This is also a gateway module because it is connected to 2 different networks. So anytime we have a module connected to 2 different networks, it's a gateway module, whether it says it's a gateway module or not. If I have a module that is connected to multiple points or more than one point of the same network. It's just a hub. The difference between a hub and a gateway is a hub doesn't translate information, doesn't change the information, just passes it through. A gateway is actually processing information. Many times gateways are dominant or master modules, but not always. So I hope that explains the other slide when I talk about talking through a gateway here. The master module will wake up the slave module for the following reasons. Another module is requesting information that the sleeping module can provide, such as sensor actuator information. Another module is sending information that the sleeping module needs, such as I need it to do something or I need information from a sensor that's connected to it. The master module determined that the computing ability is needed to operate the vehicle. So it uses the computing resources of the sleeping module to assist in carrying out difficult computer functions. Going down the road at 60, the driver's door unlock module doesn't have a lot to do, but it has some computing power. Let's wake it up and have it help us. So there are three traditional classes of CAN. These classes are defined by the Society of Automotive Engineers based on data speed of the bus measured in kilobytes per second. So CAN A, normally a single wire CAN network, has a very slow data transfer speed of about 10 kilobits per second. This class was used on early vehicle systems, but is seldom used today. Now, some of you may be old enough to remember a 14K modem. So same K, kilobits. CAN B, medium speed CAN, used for a lot of our body and systems today, has a medium data transfer speed of about 83 to 125 kilobits. So before we went to DSL and cable, we had a 56K modem. That's where modems maxed out on the phone lines, 56K. Then we went to DSL, cable, satellite, and so on. So it kind of sounds slow, but boy, it's a lot quicker than some of the stuff that was available for people trying to use the internet. So this is used for vehicles that don't require exceptional data transfer speed, body control module, HVAC. So as we build faster networks, two things happen. They become less reliable and more expensive. So manufacturers only build the network speed as fast as they need for the application. So that's another reason for having multiple networks. That way I can have some really slow networks, CAN A. I can have some medium speed, CAN B, and I can have some high speed, CAN C. And by having different networks, I can group the modules that require that communication speed together, thus lowering production costs, but use a gateway module to share information between the networks. And so if I have a module that requires high speed communication for most of its operation, but it needs information from a low speed module, it's able to get that information through a gateway module. Our CAN C, that is what the CAN is that we have at our DLC. That is what we use for OBD2 is CAN C, has a high data transfer rate of about 500 to 1,000 kilobits. This class is used primarily for powertrain and chassis systems that operate high-speed data, electronically operated throttle, steering, brakes, etc. Usually this system only has 3 modules. That's not really true. These will normally have, we see 5 is pretty common. 5 or 6 modules is pretty common today. So here's an example of comparison between A, B, and C. So here's CAN A, here's CAN B. You can see CAN C is exponentially faster. But as I said, the faster we go, the more expensive it is. So now we have CAN D, but CAN D is normally not called CAN. So CAN D normally goes by a trade name like FlexRay or MOST. And CAN D is 1 to 400 megabits per second. So now you're talking, what, high-speed internet on cable or Fiber optic, I mean, that's, you start getting 300 megabits per second. That's pretty fast. It's a lot of data. So, I mean, I know what my home internet is. My home internet is about 300 megabits coming down, download speed, but my upload speed is only about 30 megabits. So, I mean, that's a tremendous amount of data and speed. So very expensive. FlexRay is used for predominantly chassis control systems. So the ADAS we were talking about, right? A lot of information very quickly. So FlexRay is used by many manufacturers for that. Most is our media oriented. I always blank on this. But it is our infotainment system. So in the book, which I found interesting, it says that the most common thing used for infotainment is Ethernet on a car. And I got to tell you, I don't know of a single car that uses Ethernet. I know a lot of vehicles that use most, and I'm not saying none do use Ethernet. I've just never seen one break or seen one work on it, or seen one in class that I've gone to on a class on a car where they're saying they're using Ethernet on the vehicle. So I don't know where the book got that from. That has certainly not been my experience, and is not what I see. We either see a Class B network used for our infotainment stuff, which like Toyota does. You might even see a high-speed CAN C network used for infotainment, which some manufacturers do, or they're using most. But I haven't seen anyone use Ethernet. So I was really surprised that the book used Ethernet as the correct answer for that quiz question. And that's what the book says. I mean, it justifies with the text. I just can't think of an example when we're even using it, much less it's the most used. CAN gets a little confusing because we have terminology in a blender, so to speak. So I can talk about, when I say BCAN is not the same as saying CAN B. So CAN B is a speed and a protocol, where BCAN is often referred to as body CAN. Now, body CAN can be CAN A, CAN B, or CAN C. So, or CCAN, chassis CAN, versus CAN C, which is a speed and a protocol. So you see where things get a little confusing between how manufacturers use these naming. CAN high and CAN low, am I talking the speed of the network or the polarity of the wire on the network? So sometimes we really have to kind of slow down and figure out exactly what the manufacturer is talking about in their documentation, because the terms do get mixed around and confused. And there's a lot of other confusing variations. Which of the following CAN protocols works at the fastest speed for transferring data?
CAN Z.
CAN D, absolutely.
D, candy.
Yep, number 4, CAN D. Not the candy that comes in a wrapper that's covered in chocolate. So most vehicles today use both CAN B and CAN C systems to operate the vehicle. To allow these two buses of vastly different data rate speeds to share information with each other, the system employs a gateway module. The gateway acts as an interface between the different buses, like an interpreter, which allows them to share information. Usually the master module and the gateway module are incorporated into one unit. So master modules are almost never labeled. Occasionally, like on Chrysler's new network that they're doing, they just rolled it out. They're using dominant and non-dominant because it has to do with the resistance in the network and some testing they're doing. They're kind of breaking some rules, doing some new things on their brand new vehicles. And so that's where that dominant, non-dominant came from. So that's brand new naming technology. But I do like it. But most of the texts, including the book, still refer to master and slave modules. So system failure, if one of the two wires on a CAN B bus has an open or short, then the following may happen. The system will still operate, but may not function as designed. System may be slow in operation. Depending on where the open or short is located, some part of the system may not operate at all. If a sensor input from a defective section cannot get the signal to a good module needing that sensor input, then that good module may not operate as designed. such as a bad module attached to a speed sensor can cause problems with the powertrain control module outputs. So we see this a lot with ABS modules. When an ABS module goes bad because it's generating the vehicle speed, a lot of other systems are affected by that. Not just the speedometer, but also how the transmission shifts or shift quality, and so on. So there's a lot of things that rely on that information. So I can get codes in a lot of different modules, but I need to kind of ask, hey, are these other codes related to one single place, or is what they're complaining about all generated in one place? So it's not uncommon when we get codes for a network. Generally, we get a lot of codes. And that comes down to the modules that don't have the problem tend to set the code. The module that doesn't have a problem, that does have the problem, doesn't set a code because it doesn't know. So it's just like if we're having a meeting and everyone's camera's on and you're talking and your video freezes up. Everyone else in the meeting can see your video froze up or your audio dropped out. But to you, it looked normal. You didn't see that happen. And so you're not going to set a code because you talked and everything was fine. Everyone else sets a code saying, hey, couldn't talk to Brian. You know, he froze up. There's a problem there. And so that's a lot how network systems work. They rely on the other modules all watching each other. And so it's not uncommon to get multiple codes all pointing to the same module that's not communicating. So unlike a lot of things we fix on a car where the module with the code is where we need to fix the problem at, many times with networking, the module with the code is not the module with the problem. It's just pointing the finger. A CAN-C failure, it says the system is faster, but it's not as fault tolerant. So any shorts or opens may make the system inoperable and cause false dash readouts, engine temperature problems, and so on. What I can tell you is shorts are much more catastrophic to networks than opens, because if I just have an open wire, I can't communicate with anybody past the open. But if I short it like we did in the case study, now no one can talk. So shorts are much more severe of a problem on a network than an open. An open just means we can't talk with somebody or can't talk with a group of modules. A short, although depending on where the short is, some communication may be possible depending on the network, but a short will affect the entire network, or an open will only affect things after the open in the network. And if it's a loop network that has two-way communication, an open may not affect communication at all. So I could have a code for an open network, but yet I can talk to all the modules and everyone's happy. Okay, well, what it is because those modules are daisy chained and it knows the modules next door. It's saying, hey, the module on my right's not talking to me anymore. I can hear him talk on my left, but he's not talking to me on my right anymore. So I'm going to set a code that I can't talk to this module. And then dumb technician me plugs in the tool and goes, well, I can talk to all the modules. I don't know what this module's problem is. And I clear the code and it comes right back. And I go, yeah, module's just having a bad day because everything seems to be working, because I'm not understanding what's happening with the system, understanding that it's saying, really, there's a problem with the wire between us. It's not that I can't talk to it. That's what the code says. The reality is that I can't talk to it through the wire that I'm connected to it with. And that's where really, as we diagnose these things, understanding what codes tell us, because that's very different than what the code says on a scan tool, or even if I look it up in an information system. The title of the code or what the code says is very different than what the code actually means many times. So a system failure continued, and a severe CAN-B bus wire failure, both wires open or grounded. Multiple system failures can occur. Improper dashboard warning lights may also occur. The check engine light may be illuminated. So here's an example of a simplified network. Here I have my gateway module, very similar to the live screen I showed you off the Chrysler. I have a scan tool, my DLC. I have a master module. I have a CAN-C bus with 3 modules here. And I have a CAN-B bus with 6 modules here. So obviously cruise control probably wants to talk to my powertrain control module. To do that, it has to communicate through the gateway module. If I want to use the scan tool to talk to any of these modules, I need to talk to it through the gateway module. Now there are modules on a vehicle that are isolated that I cannot talk to with a scan tool, and their data is actually posted in their gateway module. So it acts like the gateway module is doing those things or has that information. In reality, is getting it off of its local network, and it is just posting all the data because the other modules in the network don't support sharing the data with the scan tool. So they leave it all to that primary dominant module. System failure continued. The gateway module or master module is constantly polling all modules to check their readiness status and their ability to transmit receive data. So if someone's supposed to be there and we poll them or ping them and don't get a response, the gateway module or master module is going to set a code. If the module is operating correctly, the gateway master module will advise all the other modules that the module is inoperative and to ignore it. The gateway master module will continue to poll that problem module and see if the correction was made while the vehicle is in operation. If the module returns to operational status, the gateway master module will inform all the other modules that this module is now operational and to accept that module's information. A module continues to be faulty or the bus wire is faulty, a U code DTC will be generated. So when we get into OBD2, there's 4 different kinds of codes that we have. We have P codes for powertrain, C codes for chassis, B codes for body, and U codes for UART, meaning network. So obviously an engineer came up with that description, not an auto guy like myself, because they'd be N codes for network, which makes sense. So the only time you hear UART is when we talk about why it's called a U code. But that is what it is. So U is my network codes. I can have B codes that cause a network problem. I can have C or P codes that are reflective of a network problem. And I can have U codes. So U codes are considered network codes, but just because the code doesn't have a U in front of it doesn't mean the network can't be at fault for the code. So here's a picture of a GM vehicle. This is GM schematic. So we have our DLC, 16-pin DLC, and it has the pin numbers. And then the pin numbers are all out here. So pin 1 is my GLAN circuit, which is a CAN-A network. One wire CAN-A network. And so it comes down here, and I can see this is a star network because I have a splice that goes to 2 buses or that are going to send out everything to these different modules. Over here, I have pin 6 and 14. It's a 2-wire network for my OBD2 high-speed CAN. It comes through a junction box, and then it is sent out to other modules, and these modules happen to be daisy chained. I got 2 wires in, 2 wires out, 2 wires in, 2 wires out, and so on. So these are my high-speed network wires. So that is how this vehicle is built. Now, I need to have some way of getting information from this network to this network, right? I mean, I got to be able to share information. My airbag is over here on this lower speed network. So what I'm going to do is I'm going to look for which modules are on both networks. And if I see my BCM here is on the high speed network, it's also on the low speed network. That means my BCM is a gateway because it's connected to 2 networks. So even though nothing here is telling me that, the definition of a gateway is it's connected to 2 networks. If it's connected to 2 networks, it has the ability to share information between the networks. So let's look to see if there's any other modules to do. Well, the vehicle control interface module is here. It's also here. So the vehicle control interface module is also a gateway module. So now I have 2 modules that can perform the function of a gateway. Are they both doing it all the time? Is one primary, is one secondary? Who knows? That's where you got to read description operation. What I can tell you is the only way I have of getting information from one network to another is modules that are on both networks. So even though this is not a topography screen, I'm able to clearly figure out who my gateway modules are. Is that helpful explaining how I got there?
Yeah.
Okay. And I put this in here specifically because we have several GM trainers at the college that use, I have a network trainer that actually uses this network on it right here and combined with this. So we actually see this, but also we have other GM trainers that are using different components from each of these networks. So that's why I put the GM in there, but also, you know, things are real simple in some of the drawings that are in the book or drawings I have in PowerPoint. And then when we go out in the real world and we try to look some of this information up, the information looks nothing like what we saw in the book. And we're trying to make heads or tails of the information we're reading and reconcile it with what I expected to find based on what I learned in the book. And that's why I like to bring in stuff like this, which is real world. This is all you get from GM, figure it out. But by applying the rules and definitions of what the components are, we can figure out the topography of this network. We can figure out what has to happen and if things aren't being shared, where the problem is. An OBD2 CAN network connects to the DLC at which of the following pins? Anyone remember?
Number 3.
Number 3.
Absolutely, pin 6 and 14. And that's a need to know because every vehicle since 2008 connects there. So there's 16 pins on the DLC. The ones I expect you to learn in this class is pins 4 and 5, which are ground, pin 16, which is power all the time, and 6 and 14, which is CAN high and CAN low. Those are the ones I expect you to know that I'll probably test you on. The fact that, pin 1 was for my GM GLAN or pin 2 is for GM type, class 2 data. Those are nice to know, but those aren't things I'm going to test you on. But this is something because it's every vehicle made in the last 14 years. And if I don't communicate that from testing, that's something that we should know. And that's why I put the question in. So my network, my high-speed network, I have my DLC, there's 2 wires. I have the modules all attached on the wires. Inside either 2 of the modules or separately on their own, I'm going to have what are called trimming resistors. So most high-speed CAN systems use 2 trimming resistors, and each trimming resistor is 120 ohms. So, and they are wired in parallel. So since we're sending a signal out from each of these modules, and the signal is sent on both lines, but the signal is opposite of each other. In other words, one side goes up, the other side goes down. In order to do that, because we're putting power on one side and ground on the other effectively, what do I need in the middle if I don't want smoke to come out? A load. So these trimming resistors act as the load for the 2-wire network. So these trimming resistors are 120 ohms, give or take 10%. They can be measured at the DLC. So if I disconnect the battery, I can go to pin 6 and 14, and 220 ohm resistors in parallel should give me an effective resistance of 60 ohms. Remember, we're allowed plus or minus 10%. So a reading of 61 ohms is perfectly acceptable. So for many manufacturers, this is one of their first tests on a network that won't communicate. Because if I have infinite resistance, I have an open wire. If I have less than 60 ohms, then I have something shorted. So this is a quick first test that many manufacturers have you do. In reality, it's not necessarily that quick. Personally, I only do this test when my lab scope pattern tells me I need to do this test. So my first tool is a lab scope. Because in order to use an ohm meter, I need to isolate everything, right? So I got to turn off the power. I got memories. I got memories of my seat, my sunroof, I'm in radios. I'm gonna have a mad customer if they lose all the radio stations. So I really don't want to depower the vehicle. I can wait an hour and see if all the computers have gone to sleep and then try to take the measurement as long as I don't open the door. That's a lot of time. So all of a sudden it's not a real quick test. So although many manufacturers, this is their first or go-to test, we really shouldn't be going here first. What we should be doing first is using a lab scope, because a lab scope based on the pattern will tell me if this is something that's possibly wrong. And so that is the thought process there. But they are measurable. You do need to know there's 220 ohm resistors in parallel, and their effective resistance at the DLC is going to be about 60 ohms. Those are need to know things. Those are things you see in tests all the time. That is that book knowledge that everyone expects you to know. Reality, you see 61.4 ohms. That's not 60, it's just close. And even though the books and a lot of factory training I've gone to, this is the first test they want you to do. Reality, not so much. You need to know how to do the test. This shouldn't be the first thing you're doing. What we use, if we have a problem where the DLC is not communicating, we would normally use what's called an OBD2 breakout box. And what this tool does is it connects to the DLC, and my scan tool is able to connect here. So now this tool is between my scan tool and the DLC. And now I have LEDs for ground and for power. I also have LEDs for each of my communication protocols. So there's these four different pins are the main pins that we're trying to talk to a computer on. And as it talks, because we go from low volts to high volts, my LED should what? Flicker. It should flash, shouldn't it? It means something's happening. So if I have an LED that's off all the time or bright all the time, that's a clue that I have a problem. And we know that we communicate on what? Pin 6 and 14. And so we have an LED here on pin 6 as we're looking at that signal. Is it trying to talk? These also have what are called banana plugs. These are 4mm banana plugs here. That is the standard plug we use for test leads for lab scopes and digital multimeters and everything else. So I'm able to plug my lab scope into here while I'm trying to talk to the vehicle. So now I've got my scan tool hooked up. I've got my lab scope hooked up. I'm going to try to talk to the vehicle that's not talking to me, and I'll be able to pretty much instantly see what kind of problem I have. To me, that's a lot quicker than taking everything apart or trying to do the test. That's only one thing that could be wrong. Why should I invest all my resources checking one thing, terminating resistance, especially when it's almost never a terminating resistance problem? So, but yet that's where a lot of manufacturers in their flow chart or in their factory diagnostic procedures start you. And that's kind of one of my beefs with factory diagnostic procedures is they don't take into account how much time it takes you to do the test or the likelihood that that's what's wrong with the car. It's just the engineers decided to do that test first. And where if I'm diagnosing something, I want to step back big picture. Which tools give me the most information with the least amount of work? Well, certainly I'm going to try to talk to the computer. How do I know that I have a problem unless I can't talk to the computer? Or I find out that I can't talk to part of the computer. And if I can't talk to part of the computer, I don't need to test for resistance anyways, because that means the network's up. There's a problem somewhere in the network. And then if I can't talk to anybody, now all of a sudden a lab scope makes sense because I can tell just by hooking a lab scope up if I have an open, a short, where my short is, do I have a bad terminating resistor, all that very quickly, literally in seconds with a lab scope. So again, it just makes sense. And the purpose here is not to make you an expert at reading the lab scope, but the purpose is to let you know that there are tools out there and there are skills to be developed that further our ability to understand what's happening on the vehicle. And so if I have a vehicle that's not working, I might be talking to the technician asking, how are you going to diagnose it? Or how did you diagnose it? Is going to kind of give you, so if you have a technician saying, hey, you know what, I need an hour's labor because I need to go do a terminating resistance check and they haven't checked anything yet, I might be putting the brakes on and going, wait a minute, why do you want to do that first? What leads you to believe that that's the problem? Ask questions just like we would in any other business. So these breakout boxes have LEDs to verify activity, test points for power and ground, and provides jumpers for circuit overlay. What a circuit overlay is that, say I can't talk to the network because the network's open. I could take a jumper wire from 6 and from 14 and take a wire and go to a module that I can get to and back probe the wire that would be connected to pin 6 and 14. In other words, the CAN positive, CAN high and CAN low that are connected to that module, and then see if I can talk to everybody. If I can, it proves the whole network's up and I just have a broken wire. So I can do things like that also. So it gives me a lot of flexibility, a lot of creativity to do different things. So again, the idea here is to expose you and show you. I actually do have some of these at the college. I'm looking forward to, of course, with the new CDC stuff, we'll see what happens this fall. But I'm looking forward to getting back where we can actually put some tools in some hands and actually apply some of the stuff that I'm talking about here. Because that's always really good, I think, for students to see those things. How many terminating resistors are required to be present on a high-speed CAN network?
Number 2. Number 2.
You got it. When measuring the terminating resistance at the DLC of the high-speed CAN network, what is the expected results?
60.
60 ohm.
You're correct, 60 ohms. Because 220 ohm resistors in parallel is 60 ohms of
60
resistance.
ohms. Mhm.
So, you know, that parallel circuit rules that you guys really hated in module 2, and why am I learning all this stuff? Here's a practical application of why we need to know it. So I do have a chart that I put in the PowerPoint. This is not in your book. You know, if you're doing any test, the purpose is, you know, we normally see, here's what good looks like. Great, so I got a broken card, it's not good. Well, what does not good mean? And that's where it really becomes challenging, right? Because we see things that are good. What we're looking at is not what we've seen, it's not good. But now that next big jump, what does not good mean? Where do I go next? What's the problem? So what this chart has is it has 60 ohms, correct? If I'm below 50, that's a low resistance, indicates a short between the CAN lines, maybe in a module, but it's almost always a circuit fault. If I'm at 40 ohms, verify the schematic, I may have 3 terminating resistors. So there's a couple there's a manufacturer, I don't know which one it is off the top of my head, that decided 3 terminating resistors is a good idea, right? So if I have exactly 40 ohms, before I jump down the rabbit hole, let's do a little more research. If I have 70 to 110 ohms, circuit or connection resistance issues or module resistance issues. 120 ohms, one of my terminating resistors is open, or the wiring going to the terminating resistor or the module with the terminating resistor in it is open. Over 130 ohms steady, circuit connection or module resistance. If it's erratic, you still got power on the CAN line. You didn't wait long enough for everyone to go to sleep, or you woke someone up trying to do the test. If it's infinite, I have an open CAN circuit on a non-insulated parallel leg. Both resistors are open, not likely. Or I have non-permanent resistors are used, which can't be measured. So some manufacturers, their terminating resistors are only connected when you turn the key on. You can't test them. You can with a lab scope, because a lab scope tests things when the circuit's complete, when you're dynamically testing something, the thing's all in one piece. An ohm meter, I got to isolate things into parts to test it. So again, going back to why the lab scope is better, especially for initial testing, than using the ohm meter to measure terminating resistance. But I did want to give you guys these numbers out of this chart. So say I don't have a lab scope. Can I still do some testing on a CAN system? Well, I can. I can still get some information. So my high-speed CAN system that we use at the DLC has a 2.5 volt bias voltage. CAN high goes from 2.5 to 3.5 volts to talk. CAN low goes from 2.5 volts to 1.5 volts to talk. and they're doing it at the same time. So the pattern's doing this. So going 2.5 to 3.5 or 2.5 to 1.5. So what we did here is we used a digital multimeter. I used the min-max setting, so it's going to capture the highest voltage and lowest voltage. And we measured pin 6, which is CAN high, and pin 14, which is CAN low, and looked at the highest and lowest voltage. So when I looked at CAN high, it goes from 3.5 to 2.2. That is a normal expected range. That's a known good. And I've seen some of them go from 2.5 to almost 4. I mean, what I'm looking for is some balance top and bottom. So as long as the amount that it goes over is the same on both CAN high and CAN low, I'm okay with it. And we see that example here because we know I'm supposed to be at 2.5, but I went all the way down to 2.2, but I'm going up to 3.5. When I look at CAN low, instead of going to 2.5, I'm going to 2.7, almost 2.8, and down to 1.5. So you can see at that 2.5 volts, I'm overswinging almost 300 millivolts on both CAN high and CAN low. Since it's the same, that's normal. If it only did it on one, then I might be a little concerned. But what does this tell me? It tells me that communication's happening on the network. It tells me it's not shorted, because if it was shorted, I'd have a steady voltage and I wouldn't be seeing this. And it also tells me it's not open going to wherever the test point is. Means there may be open somewhere else in the circuit, but the open is not causing a loss of communication with my scan tool when I do this test of the DLC, because I have network communication. So I may have bad traffic. I may have other things. I may need a more tool, but I don't have an open. It's not open at the DLC. It's not shorted, and it's working in the correct range. Does that mean it's good? No. I can have all those things and still have no communication because of other issues. That's why a lab scope is so much more powerful. But this right here allows me to what? Pick the low-hanging fruit, find something that's really broken or really wrong. So this is better than no information, but don't walk away after doing this test and say it's good. It just hasn't failed those tests, and I know what's not wrong. I don't know what is wrong. Now here, use a lab scope, and what we've done is we've taken a movie, and then I've made a small square in this movie, and that's what's on the screen. So this lab scope works a little different than what you've seen. This happens to be a picoscope. And so the scale for the red is over here. So here's 0 volts, 2 volts, 2.5 volts is right here. For blue, here is 0 volts, here is 2 volts, and 2.5 volts is right here. So you see the bias voltage is at 2.5 volts on both of these. We've just spread the scales out. So when this one goes up to 3.5, this one is going down to 1.5. So you see that the pictures mirror each other. So here's a packet of information, no information, a packet of information, no communication. So you can see these packets I was talking about. There's a packet, nothing, packet, nothing. So when there's nothing, I should have a nice flat 2.5 volts. And when there's communication, I should see that communication the same on CAN plus as I do in CAN minus, only inverted. So we can see, so doesn't this look mirrored? Everything's happening at the same time. We don't have anything happening here that's not happening here. They're going opposite directions, not the same direction. And where I have spikes or where I have amplitude changes, it's the same. This is a known good. Also, if you see here where I kind of have this darker line inside here, that's where it's hitting some averaging. So this darker line, because I'm so far out still in the picture, it's just something that happens with the digital scopes. But again, if we look at that, that's also mirrored top and bottom. So it really shows you the detail that we're able to see very quickly. This is fine. This is good. And so very quickly, I'd be able to see if it's not good and why it's not good based on what the pattern tells me. I personally like looking at pictures better than I like looking at numbers. So I really like a scope, being a visual person. Because it's always, to me, it's the game of which one doesn't look like the other. And I was always pretty good at that. You get 2 pictures of what's missing, find 5 things that are missing. I was always good at those. I like those. Reading a scope's kind of like that. What is the expected bias voltage on a network wiring of high-speed CAN?
Number 2.
Number 2, 2.5 volts. And the reason why that's important, because everybody uses a 2.5 volt bias for pin 6 and 14 of their high-speed CAN network, because that's what they're required to do by law. So that means every car sold since 2008, with 2 exceptions, is going to have the same bias voltage on pin 6 and 14, which means I can test every car, whether it's a Mercedes or a Hyundai, the same way. That's powerful information. I'm about how does the system work, not what emblem is on the hood. And because we really want to, once I know the system, now the emblem doesn't matter. So here is a low speed CAN. This is GLAN, so that General Motors system I showed you, pin 1 on one side and our CAN in the other, where I pointed out the vehicle interface control module and the BCM as our gateways. This is a signal out of the low speed network. So the low speed network, single wire network, toggles between 0 and 5 volts. So it rests at 0 volts, and then it says something and goes back to 0 volts. And then it says something again and back to 0 volts. So this is a message, and it toggles between 0 and 5 volts. So my 5 volts is right here. My 0 volts is here. And as I mentioned, a lot of times we don't toggle all the way to 5 or all the way to 0. And that's because of fault setting. The computer needs to know that if it sees 5 volts all the time, that's a problem. If it sees 0 volts all the time, that's a problem. So it wants to see that in the middle. And that's why you see us switching between about 0.5 volt up to about 4.5 volts. And that's normal. And I can have some different amplitude. This one goes a little higher, probably because it's a higher priority message. It's yelling louder. So for you to diagnose or repair a CAN vehicle, you need to have access to appropriate diagnostic manuals, technical service bulletins, and have a CAN compatible scan tool. Today, all scan tools are CAN compatible. However, if you're buying an old scan tool, it might not be. So I have a couple quick case studies, not as involved as the first one I did. So to illustrate how the CAN system is a fully integrated interactive system, here are 2 true stories. One evening, a fleet maintenance technician changed a defective light bulb on a fully functional 2005 Ford truck. The next morning, the truck would not start. And to make it harder, because it's a fleet, they had 2 shifts. So the technician working on the second shift replaced the light bulb. The technician came in the next morning who works on the first shift, unaware the light bulb had been changed, just the truck would not start. What they found is that the light bulb was replaced with the incorrect part number. Remember when we talked about light bulbs, I said it's really important to make sure you put the correct part number in, because that part number determines not only the configuration and shape of the light bulb, but the wattage of the light bulb, how many amps it's going to flow. In this case, the light bulb used a higher amperage than the original bulb. The multiplex system sensed the higher amperage draw during the system self-test at startup and shut down the fuel pump. Because just we talked about compartmentalized modules, this had a module in the back that did the functions for the rear of the vehicle, which included lights and fuel pump. So the module saw a problem. Well, we're going in self-protection mode and we are not going to start. So the PCM did this so the bus system and components would not be damaged by the bulb's high current draw while the vehicle is operational. This was not an easy one to figure out since the repair technician was not aware the bulb had been replaced the night before. Wow, that'll make your head hurt, won't it? So here's another one. Another Ford, 2004 Ford comes into the shop with the following complaints. The vehicle periodically slows down to a maximum speed of 20 to 25 miles an hour for no reason, even with your foot to the floor. And by the way, the door jar light comes on occasionally, even though all the doors are closed tight. What's the problem? Where do you go with this? We hooked up a scan tool. There's no codes. The car doesn't see anything wrong. The computers don't see anything wrong. So the computer doesn't see that it's doing anything wrong. That in itself is a huge piece of information. Computers, I love computers because they're simple, they're rational. They take an input and provide an output based on their programming. The only time they set codes is when they see an input that's outside of what it should be. Or they try to turn something on as an output and it doesn't work. In this case, we have no codes, which means the computer doesn't see anything wrong with what's coming in. And it doesn't see anything wrong with an output it's trying to perform. But yet the car loses power and will only go 25 to 35 miles an hour. So the clue here is really the door jar light. Is it possible that some engineer somewhere might design a vehicle that would limit speed if the door's open? Or potentially not even allow a car to go into gear if the door's open? Well, I'll tell you right now, the answer is yes. BMW on an M vehicle that doesn't have the regular shifter, just taps it back and forth or plus and minus with their sequential transmissions. You cannot put that in gear. It will not let you go in gear, even though you tell it to, if the door is open. Also won't let you do it if the hood's open. So manufacturers do put in those protections. We know BMW does, because I had a car that wouldn't move and I had to figure out why it wouldn't move. And I just drove it in and I had to think, okay, what did I change? Well, the door's open. Let me try that. Still wouldn't move. Okay, well, I opened the hood. Let me close the hood. Hey, the car moves now. So it won't move with the hood open. That I found that out because I drove the car, popped the hood, and then I couldn't move the car again. So I know one manufacturer does. Is it possible one manufacturer does something, someone else in the world might also do something like that? It's possible, right? So would it make sense to diagnose the door jar light that the customer says, yeah, it's annoying, but what they really care is that they can't do more than 25 or 35 miles an hour sometimes? Because it's possible that the computer might be looking at that and going, you know, I don't want you to go too fast if the door is not secure. It's not in any book, but it kind of makes sense. So they looked at the door jar light, and it's found that baby spiders had made a nest in their rear door switch, causing an intermittent poor connection. The CAN system thought the door was open going down the highway. So to protect the passenger from an unscheduled bailout at fatal speeds, the engine control module, or PCM, limited the vehicle speed to 35 miles an hour. So you see in this case study wasn't about how technical you can be. Can you use a lab scope? How good are you with a DMM? Can you read a flow chart? It was, can you step back and think about how things might work and come up with a hypothesis on what might be causing the problem to give you direction to go test. All diagnostics is gathering information, coming up with a hypothesis, and then proving or disproving that hypothesis. The mistake people make is either they don't spend time gathering information, or once they've created a hypothesis, they're so invested in that hypothesis, they're not willing to be wrong. If you want to diagnose vehicles and be effective at it, you need to be willing to be wrong. You need to be willing to go, yep, gathered information, came up with a thought, did a test. I just proved that that's not the problem. I need to go back and relook at the data or gather more data to come up with a new hypothesis to see what I need to test next. It's a very methodical and thought out process. And I apply that to a lot of things, sometimes much to the frustration of my wife, because I'm gathering data. I'm taking time to come up with that hypothesis. I'm doing that same process. And so that is the process of diagnosis. That's how these last two vehicles were fixed. It wasn't technical. It was what could possibly do it. Like I always say, if you can't fix it up here, you can't fix it with these. So as we look at network protocols, we can see here, so this is incremental cost per node or cost per module. Node's a module, and our speed. So I can see a local interconnect network is pretty inexpensive. And we use that for steering wheel controls. We use that for some other stuff. We get up faster, CAN B and CAN C. Then, boy, we jump up even faster, FlexRay, which is used for body control, ByteFly, which is an optical bus, MOST, which can be a wire or optical, and there's also D2B. I mean, see the exponential cost. So this is 10 times the cost of a LIN network, 5 times the cost of CAN C. But it does go a whole lot faster. So that's why manufacturers have different networks to do different things, because of the different requirements. And again, they're trying to keep the cost down. So that's why we see this mix of things and why we see gateway modules that allow us to share information. So with this, tomorrow we're going to finish up networks. I'm going to introduce you guys to some of these other network protocols. We're going to take a look at LIN. We'll take a look at FlexRay. We'll take a look at MOST. And just so you can kind of be familiar and kind of see some of the things that are going on and some of the different languages out there. I don't like how the book treats everything like everything's a CAN network. No, it's not. There's a lot of stuff out there. The purpose is really just to show you there's other stuff out there, not so much to make you an expert on it by any means, but just so that you don't take what the book's saying that everything is one thing when it's not, because that I think ignorance gets you in trouble. I think as long as you know there's other things out there, if you see something that's not CAN or sees, you're going to take the time to figure out, is it CAN or what's it using or what's the protocol, and that alone is going to help you make better decisions and keep you from damaging equipment or a vehicle. So we're going to finish off with that tomorrow. And then we're going to get into my presentation on sensors, actuators, and computers. So I'm going to start that tomorrow. And start really breaking it down to what's happening. Then we're going to go through all of our sensors, all of our actuators, and see how the computer uses that. And the thought process is also looking at sensors from a wiring circuit standpoint, how we test them and how they work. And again, there's not that many, so we're going to drill them down. We're certainly not going to finish that tomorrow. That'll go in and that'll fill all of Monday also, and possibly into Tuesday. Just depends on how many questions and the pace of it. And we will have, based on where we're at, I will put the test on. I'll send an announcement out later on today or tomorrow. The test will be next Wednesday and Thursday, and I'll send an announcement out to that effect. And again, that test covers everything from module 2 through module 5.